Okay, one major theme of this chapter is going to be that of matrices, and this first problem tells us to write the system as an augmented matrix. Well, the first thing we want to do is clean up this equation a little bit. So let's begin by distributing. We're going to have 2y minus 2x is equal to 4 minus 8x. And I'm going to add 8x to both sides. That would be 2y plus 6x is equal to 4. But we want our x's written first, so this would be 6x plus 2y equals 4 when that's written in standard form. This second equation, if we add x to the left, we now have x plus 5y equals 6. So here is our system written in standard form to begin with, and we want to write that as an augmented matrix, which basically says write the coefficients only in the positions that you see them in, and this will become our matrix. Now the augmented part really means that we have a square matrix on the left with this column on the right which represents the constants augmented on. To augment means to make larger. Now, if we were to solve this system of equations here algebraically, you guys know that we don't have to have the equations written in this order. If I had written that second equation first and the first equation second, the answer would not change at all. Basically, this means that I can interchange rows of a matrix. If this matrix represents these equations, I could have reversed the order in which I wrote those two rows. You also know that we can do elimination to solve a system, and for example, if we want to eliminate the x's, we could multiply that second equation by -6 and then add the equations together. In other words, you may multiply a row by a non-zero scalar. You can also add a multiple, this is our next blank, a multiple of one row to another row. Okay, so those are going to be the row operations, 1, 2, and 3, that we're allowed to use. Now basically, we are going to be doing row operations, and our goal is to get the following. We want to have a matrix that has a 1 in the top left corner with zeros beneath it, and if we have 3 equations, there'd be 2 zeros beneath it. We then want a 1 in the second row, second column, with zeros above and below it. And then we want a 1 in the bottom right corner with zeros above it. And then there will be 3 numbers here on the right, which I'll just call x, y, and z. And if we can get our matrix into this form, basically this means x plus no y's plus no z's equals whatever number is there. So we'll have our answer. This is what x is. This 1 is in the y column, so no x's. Yeah, 1y, no z's. Y equals whatever this number is, and likewise z equals this number. So ideally, we want to have this diagonal with 1's on it surrounded by zeros, because then we can just read off our solution set. Now, the first thing we want to do is get the 1 in the top left corner. So I will call that process A. We then want to get zeros beneath it. I will call that process B. Followed by getting a 1 in that second row, second column. That'll be process C. Followed by getting zeros above and below that. That'll be process D. We then want a 1 down here in the bottom right corner. That will be process E. Followed by zeros above it. That'll be process F. Every problem is done the same way. What I'm going to be describing here is what's called an algorithm, a process for solving this system, and computers are actually very good at doing this. Now, let me write out a couple of descriptive rules here. I want to say to get 1's, and that's what we're trying to do here at steps A, C, and E. Basically, I want you to multiply that row by the reciprocal of the number in the position you want the 1. In other words, let's say that 1 was a 6 and you wanted the 1 there. You would multiply through by 1/6 on that row. To get zeros, I'm going to say multiply the row with the 1 by the opposite of the number you want to cancel out. Then add the rows together. I know this sounds kind of vague right now, but this will make sense once we actually start doing some problems.